Hello there and welcome back to this video series on control systems. Over the past few lectures, we have been looking at um, force voltage analogy, and we have also seen what we mean by voltage scaling factor and current scaling factor, which are used to reduce the magnitudes of voltages and currents that we need to deal with. We have also seen that we can adjust the time scaling so that events in mechanical systems occur either at a faster rate or slower rate. We call it time scaling. Okay. This force voltage analogy is also called direct analogy. Going through this little video, a student will be able to specify what is meant by inverse analogy and identify analogous quantities in mechanical and electrical systems in inverse analogy. And we see that inverse analogy is also a force current analogy. It would be best if you watch videos 16 to 19 and then 21a to c before going into this video. That is, if you continuously watch 16, 17, 18, 19, 21a, b, c before going into this video to make the most out of it. Similarly, if you solve a couple of problems, maybe 3 or 4 on electrical circuits and spring vase damper systems before going into this video. This video is kind of short one. We won't be seeing a lot of details here. We'll just see how this inverse video comes about in the form of writing equations just a little bit differently, and we identify what are the analogous quantities. So with that, we'll jump into the video. In the case of direct analogy, that is force voltage analogy, we have seen that force is analogous to voltage, inductance is analogous to mass, and so on and so forth. So we call it force voltage analogy. In this analogy, that is inverse analogy that we are going to see, we'll try to strike force as an analogous quantity to current in electrical systems and thus call it force current analogy. So to begin with, we will see a simple RLC circuit where RL and C are in series, and note that this total potential drop is the sum of drops across resistor, inductor and capacitance, and that is, we write the equation V of t is drop across inductance, that is L di by dt, drop across resistor Ri, drop across capacitance. That is, we can use the notation capital D, differentiation operator is d over dt, and thus reciprocal of differentiation operator is integral dt. We can write this equation as written here. This forms more or less the basis for inverse analogy. We consider a mechanical system as shown here. You can see force is acting at one end of the system and mass is at the far end from the point of action of the force. So you have force which is acting at one end of the system where you have spring, damper and mass in series. Note, earlier we have seen that mass cannot be in series anywhere else except at the far end. That is what we mean. Force is here at the complete end of the system, that is spring, mass, damper, you have mass. Thus this mass can be in series. Now recall that when elements are put in series, you find the net impedance of all these elements to be reciprocal of sum of the reciprocals. That is, each spring contributes a K, 1 by K, this 1 by BD plus 1 by MD square, the reciprocal of all these. So we take what is in the denominator, this quantity, onto the right hand side and write this whole thing acting on F is equal to X. X is the displacement. We'll do a little trick here. We'll apply the operator d by dt, that is differentiate on both sides. To get here you have x dot and an additional d is multiplied here. So dx, that is dx by dt, which is x dot, is equal to d acting on all these, that is d by k plus 1 by b plus 1 by md. Now we see that this equation is very similar to the electrical equation we have seen earlier. We'll try to put the electrical system and mechanical system side by side to note the corresponding positions and similarity very clearly. This equation is for electrical system. This equation is for mechanical system, SMD system. We note that the series parallel connection is not reversed. Here also the elements are in series. Here also the elements are in series. Further, we note that the force is analogous to current. Force F of t analogous to current. And we see that velocity, voltage is corresponding to velocity. And also we see that mass is analogous to capacitance. Kindly note, we are comparing the elements that are in corresponding positions. Coefficients of d, constant term, and coefficient of 1 over d, and so on. Similarly, we notice that 1 over b is analogous to r. Note that we are using the red color to indicate that the analogy leads to reciprocal. That is 1 over b is analogous to r. Similarly, the next kind of analogous quantity we can note, 1 over k is analogous to L. That is the reason why I have indicated in red here. 1 over k here, L here. 1 over b here, r here. So with this, our inverse analogy scheme is complete. Note that in direct analogy, that is force voltage analogy, the series parallel relation got reverted. Whereas here in inverse analogy, the series parallel connection is not reversed. So force current analogy, series parallel connection is not reversed. We won't give proofs of this, but we'll just state it here and leave it for the student to prove that when scale factor Ke is used, Ki is used with the understanding that F is equal to Ki into I, X dot is equal to Ke into E, and time scaling A is used, then R, L, and C can be given as shown here. We won't try to prove it, but it is kind of easy to prove it just by following a few simple things that we have done in direct analogy. So to summarize, we have seen that inverse analogy is another type of analogy in which series parallel arrangement between electrical and mechanical elements does not occur. And also we can have a current scaling factor and a voltage scaling factor along with time scaling to achieve such relationship between the electrical and mechanical quantities. That's all for now. Have a great day.